All right, so as promised, another fruit fly example. We have a colony of fruit flies. They're exhibiting exponential growth. So that kind of sets up the formula for us. We know the initial size of the colony is 100, and it doubles in size in 9 days. All right, so first of all, we want to determine the growth constant, K. All right, so let's look at this. Let's look at this equation and see what we're given here. So first of all, we know we're exhibiting exponential growth. So that part tells us basically what our function is going to be. It's going to be p of 0 e raised to the k times t. We're also told the initial size is what? 100. So that tells us p of 0 is equal to 100 in our equation. And then we're also given that our population doubles in 9 days. So the population at t equal to 9, if we start with 100, it should be double our initial population. So you could set that equal to 200 if you want, but sometimes it's helpful to leave this a little bit more general like this. 2 times our starting population. It doubles in 9 days. And we're going to use all of this to find our growth constant K. All right, so let's start here. So we'll start with our population function. And let's evaluate this at t equals 9. Because that's some information we're given. We're given our initial population, but then we're also given the population after 9 days. It's going to be double our starting population. So that's why we're evaluating at t equals 9 here. So if we plug 9 in, we get p of 9 is equal to our starting population, e raised to the k times 9. So we're plugging 9 in for t. And then since our population is doubled, we know this should be equal to 2 times our starting population. So we set that equal. And what this does is this gives us an equation that we can solve for k. And that's what we do. We solve that equation for k. So let's set it equal, set it up. P of 0 e raised to the 9k is going to be equal to 2 times p0. Now p0 is just a constant, so we actually know what it is. So if we wanted to, we could fill that in. But in either case, we want to divide both sides of this equation by our starting population. And what we see is that it's just going to end up canceling out anyways on both sides. So this gives us e raised to the 9k is equal to 2. And then to get rid of that exponential function, what do? We apply natural log to both sides. And natural log and natural exponential cancel out. And so we're left with 9k is equal to natural log 2. And then we divide by 9 to get k. And so this gives us k is equal to natural log 2 over 9. And we found our growth constant. Now, we were given this information that the population doubles in size every 9 days. So we could have also used this alternative form for our exponential growth equation, where it's p of 0 times 2 raised to the little t over the time it takes for our population to double. And if we're thinking of it in terms of this alternative format here, well, then the growth constant k is equal to natural log 2 divided by time capital T, the time it takes to double. And that's precisely what we found. We found our population doubles in size every 9 days, and this is what we found for k. K is equal to natural log 2 over 9. So just kind of checking this out here in our example. All right, so that's part 1, determine the growth constant k. Now, in part 2, we want to know how large is the colony going to be after 41 days. Well, let's write down our nice population formula now. So our initial population is 100. So we're just plugging in the pieces now into this population formula that we have. So P0 is 100, so let's fill that in. Then we have E, and then our growth constant is natural log 2 over 9. So this will be natural log 2 over 9. We're filling that in for k. And then multiply by our time variable t. So to answer this question, how large is our colony going to be after 41 days? Really, this just says plug 41 into this function and see what you get. So there we go. And the units here are fruit flies. So this is approximately 2,350 fruit flies. Units. So after all, this is just a model. So it's going to be, it'd be weird to have fractional decimal number of fruit flies. So we're doing a little rounding here to keep things in whole fruit flies. But this gives us a way to model the population size. So to get the colony after 41 days, we're just plugging 41 into this function. And the only thing we want to be careful of is when we first found this growth constant k, we were using our time variable. Our time was in terms of days. And we just want to make sure that when we plug a value in for little t, that it's also in terms of days. All right. Let's try part 3. How fast is this colony going to be growing after 41 days? Well, what does that mean? When we see things like how fast is it growing, that's talking about a rate of change. And what that really means is calculate the derivative. And we want to know what's the value of our derivative after 41 days, or at time equals 41. So we want to calculate P prime at 41. And there's a few ways to do this. So we do have our exponential growth setup here starts with our differential equation. So if we have something that's growing exponential, what that really means is the rate of growth is proportional to the size of the population. So P prime is equal to constant k times our population. So in particular, this is true for all t. So if that's true for all t values, then yeah, it's definitely going to be true for t equal to 41. So P prime of 41 is equal to k times our population at time 41. Well, part 1 was find the growth constant. Part 2 was find the population. So we just put all that together. So what did we find for k? We said that was natural log 2 over 9. And then what did we find for our population, P of 41? Right here, this 100 times this exponential. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . And what are the units on this derivative? Well, since P is measuring fruit flies, the units here are going to be fruit flies. And because this is a derivative, it's going to be the unit for our population divided by time. So, and our time is measured in days. So what this value is saying here is this is approximately equal to, if we calculate it out, it's approximately equal to 181 fruit flies per day. Nope, not fruit days, fruit flies. So after 41 days, our population is growing at a rate of around 181 fruit flies per day. So if we let one day go by, so on day 42, we would expect there would be about 181 extra fruit flies. Well, that would give us an estimate. All right. So that's just giving us that instantaneous rate of change right at time t equal to 41. What does it look like? How fast is our population expanding at that time? All right, so for part 4, we want to answer the question, at what time will our colony contain 800 fruit flies? Another way to actually back up to the third one here. So this solution, we used our differential equation. That's what we're using here, is this differential equation to help us figure out the derivative. Perfectly fine. But another option that we could do is we could just calculate our derivative from, use our derivative rules. So we could also just calculate that derivative directly. So we have, just going back, we have this exponential function. Just use some chain rule to calculate the derivative. Another way to do it. So if you didn't want to rely on this differential equation, you could just calculate the derivative directly using chain rule. Perfectly fine. You get the same answer. All right, so yeah, now let's figure out what time we're going to have 800 fruit flies in our population. And so what we want to know, what this is really asking, is when is our population equal to 800? So we're going to set our population function equal to 800 and solve for t. All right, so let's take our population function, which was 100 e raised to the natural log 2 over 9 times little t, and we want to set this equal to 800. And so this gives us an equation then that we can solve for t. So once you start doing these, the equations are it's gonna feel like you're solving, it's the same solution techniques for a lot of these. So divide both sides by this constant in front of e. So I'd probably divide both sides by 100. That would give me e and leave space, because we know how we're going to get rid of that e in just a second. So e raised to the natural log 2 divided by 9 times t. And then 8 on the other side, leave some space there because we know what's going to come next. We want to get rid of this exponential, so we want to solve for t. So what we're trying to do in this equation is we're just trying to work our way, kind of unravel all of these pieces until we get to this t. So first thing we had to do, get rid of the 100. So we divided it to the other side. Next, we have to get rid of this e. How do we get rid of e? Apply natural log. So we're going to apply natural log to the left side and then to the right side. Natural log cancels with the natural exponential function. And then this gives us the equation natural log 2 divided by 9 times t is equal to natural log 8. So we're working our way through. We want to get t by itself, and this whole big thing in front is just a constant. So just multiply both sides of this equation by the reciprocal to get t all by itself. So if we do that, we get natural log 8 on the right, and then the reciprocal, 9 divided by natural log 2. So natural log 8 times 9 divided by natural log 2. And that simplifies. If we wanted to play some games, that actually does simplify. And it actually is equal to 27 exactly. So after 27 days, the size of our population is going to be 800. All right. So right here we just multiplied by the both sides of this equation by the reciprocal of natural log 2 divided by 9. All right, so some fun games to play with these exponential equations. All right, so that really covers it for exponential growth. What we're going to see next is what happens if this constant k is not positive anymore. What happens if that constant k is negative? And we're going to get what we call exponential decay. So we'll see you there.